The project Interdisciplinary Collaborative Learning and Teaching for Resilient Wood Resources and Innovation in a Digital World is co-funded by the Erasmus Plus program of the European Union. The project is co-funded under the strategic partnership of Erasmus Plus with the duration of 36 months. We say that with Wood Plus, objectives are targeted, opportunities are taken, and make a difference under the Erasmus Plus umbrella. Activities are conducted by a consortium of 4 partners: Mendel University in Brno, Czech Republic, acting as a coordinator, University of Natural Resources and Life Science, Vienna, Austria, University of Hamburg, Germany, University of Ljubljana, Slovenia, and an associated partner, InnovaWood from Belgium. Wood Plus objectives are to support the additional inspiration of the new generation of researchers, to raise the awareness of a wide range of material application, to redesign the learning environment with innovative online modules, to individualize and internationalize the learning pathways. Wood Plus aims to strengthen collaboration in the field of wood science and technology, with particular focus on less used wood species, to achieve brain circulation for students and researchers through strengthened language competencies, to contribute to future-oriented curricula with a broader focus on tree species diversity, to develop green sector skills by promoting industrial exploitation of less used wood species for high value chain utilization by focusing on innovative material developments. Wood Plus also aims to stimulate and support students and researchers' creativity by fostering education diversity networks, to take advantage of diverse educational and research backgrounds, to foster digital competencies by pushing distant learning and innovative learning methods. Wood Plus activities include intellectual outputs such as webinars, ebook, virtual laboratory, experimental design and data analysis, multi-prior events such as conference, and learning, teaching and training activities such as summer schools, workshops, and long-term teaching assignments.
Right, so I'm from Tescan, and when I was asked to give the talk, I was really honored that I can give the first talk and that I can speak about electron microscopy. So as I guess like a lot of people from the audience know, so I have a background in wood science. So wood science is still very close to my education and education background. But I became an electron microscopist and electron microscopy marketeer by heart the last 7-8 years. That's what I do. I do electron microscopy, and I focus on the product marketing of the electron microscopy. And I think this kind of presentation is something what may be interesting to the audience of yourself. So I'll introduce the scanning electron and focused ion beam microscopy applications in the field of material sciences. And I will mention a couple of use cases from the wood science field of applications as well. So it's better connected to what one could do with scanning or focused ion beam electron microscope. So what is the goal of the day? So I basically hope that at the end of the presentation, you will end up with more information than you actually joined the presentation. So I set up 2 goals for myself. So I hope that you will realize the pitfalls of the 2D, that means surface electron microscopy characterization when it comes to the contrast methods, that it's not so trivial and that some of the contrast methods are more interesting than the others. And how they can be used in your field of application, that is wood sciences or natural natural materials. And the second goal is that you will realize and learn why the material scientist wants to characterize the samples in 3D using focused ion beam, how they can do it with our focused ion beam, and how that can be relevant to your field of application. So if you could answer these two questions at the end of the presentation for yourself, that you really learned that, then I really hope that my presentation is a success. So at the beginning, I would like to introduce the TestScan because that might be a little bit less known to you. So what is TestScan? So TestScan is the company where I'm proudly working for a couple of years. It's actually 7 or 8 years already, and it's the company who is developing, designing, producing, selling, and delivering and servicing electron microscopes and any related instrumentation. So it was founded by a couple of engineers 30 years ago, which basically would be called a spin-off nowadays from a Tesla. And that's how they founded a TestScan. So at some point of the day, they developed the first microscope and start selling it. And decade later, they joined forces with Orsay Physics, which is a French company who is the original founder of the focused ion beam. And we merged and created TestScan Orsay Holding. We're a global company. We have the headquarters here in Brno. So more than 30% of electron microscopes come from Brno. It's not because of TestScan, of course, but it's also because of our biggest competitor, Thermo Fisher Scientific, who is also placed here. But Brno itself is really considered as the Silicon Valley of the electron microscopy. We have many daughter companies across the globe. So we have 3 units in the USA. We have 1 unit in Brazil. We are across the Europe. So we have a TestScan UK, TestScan Germany, TestScan France, headquarters here in Czech Republic, in Brno, where we also produce our electron microscopes. And we have also 2 daughter companies in China. So, and this is the portfolio we design, develop, and deliver and sell. So we have a big portfolio of the SCMs. So Vega, Mira, Clara, and Magna are all the technologies you can apply for scanning electron microscopy. We have FIB-SEMs. So once you put a focused ion beam column on a SEM, it becomes a FIB-SEM. We have 4 types of those. These are on the bottom of the pages. We just introduced and are very proud of our TestScan Tensor, which is a dedicated STEM. And we have also micro-CT portfolio. And over the 30 years, we also developed a couple of special solutions dedicated to process mineralogy, geosciences, inspection of extremely large health samples in the semiconductors industry. We integrate the Raman on the scanning electron microscopy. We have a ultra-high vacuum FIB-SEM called Nanospace, which is mainly nanoprototyping applications. And lately, with the energy materials boom, we are more and more focusing also on glove boxes and how to interface a glove box with the inert transfer system with our SCM and a FIB-SEM. So this was the introduction, but now let's dive into a topic of the material science and how scanning electron microscopy and focused ion beams is relevant to the material science field of application. So I was always thinking, how to easily describe what we are actually doing with the scanning electron microscopy in material science. So it's a materials science, so there are a lot of materials, but single science, right? So what is the ultimately most precise description of what we do? And I think that what we really do with the electron microscope and focused ion beam is that we characterize in great detail features which are really critical for determination of the material's quality. So if you think about it, we have every material has its structure, has its properties, and has its performance. And those 3 things are somehow interconnected. And once you start investigating in any area of these topics, you characterize your materials. You can evaluate the performance, you can evaluate properties, and you can evaluate structures. And you can technically do all of these with some scanning electron microscope or with the focused ion beam. So this is why we call it material science, because all of the materials can be described through this using electron microscope or focused ion beam. So when it comes to scanning electron microscope, the main thing what you do with the scanning electron microscope is the SEM imaging and material contrast characterization. Here I would help myself with the current suite illusion. So if you look on the image, this is really not so much relevant to the electron microscopy. So first thing, the image quality is pretty mediocre. But if you look in the image, you rely very much on the contrast. If you look on top or at bottom, you would definitely tell, well, these two things are different. One is, let's say, whiter, and second one is darker. But if you cover this region, you realize that it's not. Both of them are exactly the same. So this is a pretty famous current suite illusion. It has a lot to do with this interface between. But what I want to tell here is that your judgment about contrast is important, and that on the first glance, you may have very bad assumptions about reality without really realizing it. And that's very, very important in electron microscopy, because electron microscopy is unique in a way that it provides you the information strictly based on contrast, and your judgment is done strictly based on contrast. And you better be knowing what contrast you are observing in order to make a proper judgment about your material. So I stole this image from a blog post about electron microscope. Whoever is working with the electron microscope will be very annoyed with this image because it's all over across the learning materials. But yeah, when you hit the material with the primary electron beam, it emits a lot of data, basically, or a lot of characteristics which you can analyze and get the data from. So the most commonly known are the secondary electrons and backscattered electrons, which describes topography or material contrast. But you have also auxiliary electrons, you have characteristics X-rays, you have catoluminescence, fluorescence X-rays, and differently scattered and transmitted electrons. And it's actually up to the electron microscopy designer how and where they put what kind of detector to obtain specific contrast, right? So there are, of course, different ways how the secondary electron and backscattered electrons are produced. Let's say the most easy way how to explain that is on the right-hand side. So either the electron is emitted from the material, that's why it's called secondary electrons, and it usually describes topography, or it's really the original electron from the primary beam and it just goes into the atomic structure of the material, and exactly this, it's backscattered back and it is detected, and it is specific for material contrast. So you can tell two different materials apart. And those are the most basic and most, let's say, known material contrasts which you could use. So this is the image which you get from the secondary electron. So it's a surface of carbon nanotubes, acquired at low accelerating voltages, and you can see all the tiny details on the surface. So these kind of nanotubes are usually put in different composites in our case, right? We put them and we believe that they enhance a lot of properties. So when we speak about characterization, it's important that we see what the structure is, how long they are, how wide they are, what the surface is, and whether it adhere well with the composite. But there are not just these images, which you could see on left-hand side, which is topography, but there are also those which has importance when it comes to additional contrast methods. So I just want to mention that there are primary contrast methods. So you have surface, which is the secondary electron imaging. You can describe phases with backscattered electron imaging, or you can describe a photon emission. So for example, in mineralogy, when you want to see zonations of the grains, you use the CL. So those are three primary contrast methods, but you have also secondary contrast methods. So you can basically divide each of these contrast methods to its secondary contrast methods counterpart. So it depends where you place your detector, and that affects the shadowing, and it provides you better visibility in the bottom of the sample. With the phase contrast, it's not just about telling apart two different materials, whether it's iron, aluminum, or some carbon material. It also can describe the channeling contrast, so that's crystallography, or you can basically use energy filtering to enhance some contrast, and photon emission also can be wavelength selective. So it's not that you would just describe the CL contrast, which you can see in the image on the right-hand side with the zircon, where you can see the zonation, but you could tell apart also different species of those materials using selective wavelength detection. So I wanted to mention the energy filtering because it's A, super exciting to see the images, and B, it's also easy to explain and super relevant to what we could do. So this is the typical backscattered electron image of the phase of the material after a scratch test. So if you have a material and you have a tiny coating on it, you apply a scratch test, and you would want to see how much of material adhered to the substrate, right? And on this image, whatever is dark, you would say it's the origin layer, and whatever is having different contrast, so a little bit whiter or brighter, it's the substrate. And you would calculate percentage, and you would say, well, it was pre-resistance or so. But if you apply energy filtering capabilities, you see that some of the features of the material change phases, and they are revealed. So here we just applied energy filtering for incoming backscattered electrons, and you see change in the phase, and you get very different information. So that's what I was talking before, that on the first glance you may have made a bad judgment. So this provided additional information, and you could see that there are way more of the origin layer adhering to the substrate. In this case, it was the iron-based, some alloy. You could use the secondary electron image on left-hand side, where you could see all the features, but you can't tell really, you can't tell the materials apart. So you really need the energy filtering to give you an idea about what is what. So how that works and how does it work? So I will explain a little bit how this interaction gives you this image. So in theory, you have two types of scattering inside of the material when it comes to backscattered electrons. So when the primary beam hits the material, it can either go around the atom of the materials, and it doesn't lose a lot of energy just by the fact that it doesn't interact with the atoms in the material. Or we have inelastically scattered backscattered electrons. So they travel deeper in the material, and they, by the fact that they travel deeper in the material, they lose a lot of energy. So imagine that you have a primary electron energy of 1 kilovolt, and it wouldn't lose energy. The escaping energy would be still 1 kilovolt. If you have inelastic scattering, it would have 1 kilovolt, it would lose 500 volts, it would have 0.5 kilovolts. So that helps a lot, because when we have a detector, we can put a specific bias on the filter beneath the detector, and we can just detect those electrons which has higher energy and therefore didn't travel inside of the material too much. And that's what we did on that sample. So we really detected just those electrons which were on very surface of the sample, and therefore had enhanced surface sensitivity and contrast. So I would like to finish up this imaging session with the wood-based use case. So I took one of my own. So actually, how I used the electron microscopy in the past was that I explained the effect of materials anatomy on the mechanical properties of wood-based composites. So this was just one of the way how to explain why some of the properties of wood-based composites are worse. Of course, there are many other effects, but the morphology is definitely one of those. So in one of my work, I created a lot of composites from different materials, but not wood. And they are used in different parts of the application, so they can be used in wood building, furniture, doors, windows, whatever. And and the idea was that since there is increasing demand for raw material such as wood, which you can use in very good ways without really making a particle board out of it, there might be interest in investigating plant-based alternatives. The problem here is that when you put something else than wood, it decreases the properties compared to the wooden-based particle board, right? And of course, there are many important characteristics that may influence final mechanical properties, but one of them is the morphology aspect. So that is how the raw materials differs compared to wood, what data I can obtain from the image, such as porosity or the adhesive penetration. So on left-hand side and right-hand side, there are two SEM images. And on left-hand side, you can see that the image is totally different than on right-hand side. And you don't need to be a genius really to tell that on right-hand side is completely different material. So you could see that there are bigger pores, that the cell walls might be different, and that also it consists more of the features, right? You can zoom in on specific part, and on the left-hand side, you can see a typical structure of wood, and you don't see a lot of delamination, for example. You could see all the cell walls pretty clear. On the right-hand side, you can see that cell walls are way thinner, therefore they can break easily, and that the porosity is way bigger. So that is one of the key morphology aspects which you could tell that it may affect mechanical properties of the material, so the material structure itself. Another point is that if you have wood-based composites, it's bonded somehow with adhesive. So you could start observing how the adhesive penetrated through the cell walls, or what the interface looked like. And on the wood-based composites, you can clearly observe some of the parts where the particles are joined together, and you can identify the bond line. On the right-hand side, you can see alternative particle board where the adhesive, for example, just glued together some softer parts of the material, and you barely found some of the bond lines. Or you could see how the interaction between the particles were on left-hand side, but that they were not really crashed and compacted. And you can observe on the right-hand side that was not really a truth for the alternative particle board, where the compaction was significantly higher. So all of that can help you and describes you clearly the structural properties of anatomical elements and how they may contribute to the final properties of composites. You can really analyze the interfaces of the porosity and evaluate differences between two samples. Well, that really enables you explaining all the mechanical properties, why they reduced, and what can be the root cause of that. And the good thing is in the electron microscopy that all of that currently can be done without sample preparation. So these samples were not golden coated. You could really use different methods to observe these kind of samples really, really quickly. I promise that second part of my presentation will be focusing on a FIBSEM. So if you see the word FIBSEM, it definitely contains the word SEM. So we definitely all know what the SEM stands for. It's a scanning electron microscope, and FIB stands for focused ion beam. So now we have already indications that there are two beams in play. So why would we need a FIBSEM? So here I will help myself with the learning iceberg. So you can see this image all over the world explaining different weird stuff, and I stole it to explain this stuff as well. So really it's difference between what you think is on the surface and the complexity behind it. It's really on the subsurface. So if you observe something on the surface with the SEM, you may have already good idea how it is relevant to your research. But if you want to explore more of the complexity, it's usually hidden beneath the surface. So a focused ion beam will get us from the surface to the subsurface problematics of our materials. So I used two images. Left one is the image from our FIBSEM. So it's the image inside of the chamber of a FIBSEM. And you can see that there are a lot of stuff inside of the chamber of a regular FIBSEM. So we have a SEM column, which gives us this imaging. We have focused ion beam column on the left-hand side, which do the milling. We have two detectors, SE and BSE, which we use for detection and therefore for the imaging. And we have a nanomanipulator. So we can do a lot of interesting and exciting stuff with our FIBSEM. We can lift out stuff, we can nano prototype stuff. We could really use the FIB system as the micro laboratory. But the essential what the FIB does, it actually accelerates ions towards the material. And through that, it sputtered the material. So for example, you could use different species, but in one of them is gallium. Second one, which we could use is the xenon. And through that, we remove the surface of the material, but not randomly. We're really scanning across the small area of interest at the nanoscale. So our spot size is, a couple of nanometers big. And therefore, it enables us to cut very small cross sections at specific areas of interest. And it emits secondary electrons, but it also sputter out the original material. Yeah, there are some implantation and redeposition, but in general, you can really mill through the material whatever you like, which is all great. So we have materials which we can observe from the surface. So left-hand image, you can see the cast iron. This is the nodular graphite on the cast iron, how it looks. And you could see, well, it's pretty clear that it's a fractured surface and that the ductile cast iron is not featuring anything which is too relevant when it comes to porosity or stuff. You could just describe the fracture. But if you use the focused ion beam on this exactly the same material, you can make a cross-section of this graphite nodule. And you can see that even the graphite nodule has its own structure, like inner structure. It has its own porosity, which you couldn't see when you observe it from the surface. But it also have the dendrite structure and initiation point where the nodule has been grown. So what you could do more, you can continue to slice and view, or you can slice a thin slice and acquire an image. And you can take this data set and you can reconstruct the whole nodule. And you get this 3D volume reconstruction. And you can really see what the internal structure of such a nodule look like and where the initiation point of this nodule is and how the growth has been driven when the material was developed. So all of that is the complexity which I was talking about earlier. So it's not only about imaging, but at this point, we are really talking about complex description of very small feature. You can see that this feature is as small as a couple of microns. We have two systems in our portfolio. One is gallium FIBSEM and second one is a plasma FIBSEM, and they are both very relevant to the material science. Both of them has its own place, but for now, you could just remember that one of them is able to mill really large cross-section in the real world scale. That's right-hand side, the plasma FIB. So you can really mill large 1 millimeter wide cross-sections. And the second one is focused mainly on the at the nanoscale. So it can do smaller cross-section, but it can do it way more precisely when it comes to real small nanopatterning applications, for example. And the trick here is that these cross-sections were milled exactly with the same time. So it's usually within 1 hour or 1.5 hours. So as I promised, I will always feature some wood-based use cases. So I, again, used some data of my own, how you can apply a FIBSEM into the wood-based wood science. So you can, for example, understand the enhanced properties of some wood anatomical elements for potential bioinspired structures. So I've never been a wood anatomist, so I know that there are wood anatomists in the audience. So if I say anything wrong, I'm just sorry in advance. But yeah, in general, there are trees which reach enormous heights and withstand significant stresses in various environmental conditions. And one of the elements which is responsible for mechanical properties are tracheids, right? So for example, Douglas fir can be around 100 meters tall and has a special tracheids with a spiral thickening. Well, and these spiral thickenings can be developed also on the European wood species, and some of them have it by default, so to speak, or it can be also developed in the stress wood. You can see clearly the spiral thickening on the right image on the right-hand side, and also you can already see a structure of the cell wall, for example. So this is all great. We see that from the surface. We can describe that it is there, but we really can't describe it in 3 dimensions and see how the spiral thickening is behaving when it's subjected to the stress. So what we can do, we can prepare the 3D tomography using a FIBSEM. So again, there are 2 problems. These tracheids can be very small, so you may not necessarily describe that with the micro CT to a certain detail. So you can use a micro CT. I don't say that you can't, but on a small, it will probably not always acquire the smallest tracheids. So you could use a FIBSEM, do the reconstruction, and you could apply a finite element modeling to this model. So we quickly did a finite element modeling of such a structure. So we used this reconstruction, mesh that, add basic properties to it. So we have defined the geometry, we have defined the placement, and defined all the conditions, and we observed how the strain develops. And you could see that in these tracheids, you have minimum strains. Oh, sorry, in this spiral thickening, you have minimum strains, and in the cell wall, you have maximum strains. So it seems that in the tension, the spiral thickening really works as a support. That's also somehow reflected with the stress. So these spirals, they have maximum stress, and the spiral thickening has a minimum stress, while the cell wall has the maximum stress. Of course, there is a pit, and the biggest stress was in the pit, which here could be seen as a defect in the wood. The one example which we published was that you could use this system in a really complex way to understand the strength of the wood at the nanoscale. So if you think about it, what is the ultimate strength of the wood? It's really defined by the cell wall, right? So it differs, it's like a multi-scale problem. If you take a big piece of wood with all of its porosity, with all of its properties, they are defined still by the cell wall. So if you would remove all the porosity and just stick with the cell wall, that would be ideal case. So something like that has been tried, I would say, for many years, has been published across different papers, that if you compress the wood and get rid of the porosity, and you basically be able to chemically fix the material, that the porosity will not occur anymore, you would get the ultimate strength of the wood. But what is really the strength of the cell wall, which creates the structure of the wood and is responsible for the ultimate strength of wood? That's something what we tried to do in one case. So you have a material like this, where you can really clearly see the vessel in spring wood, light wood, you could see the cell wall, or you could see the ray. And we are interested in the wood cell wall. So what you could use a FIBSEM for is that you could create a micropillars like this. So you could focus on specific area of interest and create small pillars, which you could test afterwards inside of the system like this. So we use the focused ion beam to create smallest compression specimens, which were, I believe, not something around, but 10 micrometers wide. And we put a nano indenter with the compression head on. We focused on the micropillar, we compress them and basically make this micro mechanical test. And you really get what you would expect you get from any mechanical test. So you get these graphs with load and depth, so displacements and load with the micronewtons. And you can observe also the deformation of the micropillars. So this is how the test is done at the nanoscale until the failure. And what we did was that we specified all the regular properties, so strength, modulus of elasticity, and we also matched that with a mapping from the nano indenter and see what the difference was. But if you would want to be very general, you could say, well, the ultimate strength of the cell wall is 276 megapascals plus minus 18. And that's not given by the nano indentation, but really something which almost replicate regular compression experiments. So this is what you can get if you ever want to achieve ultimate strength in the compression with the material like wood is. And if you compare it to the other materials, the structural steel has 400 megapascals, cast iron have 200, aluminum has 110, and human bone has 170 megapascals. So the strength of wood is superior to many of the materials which we are currently using in material science. So what was the technology behind here? Well, we use the focused ion beam, and we integrated the nano indenter inside of the chamber, and we could do all of these experiments on our materials. So it just gives you an idea that it's not just about focused ion beam, but it's also about setting up experiments, and you can modify the system according to the researcher's need. So that was my last slide. I hope that you found this interesting and that you understood how we could leverage SEM or FIPSEM in our materials. And if you are interested, feel free to go on our webinars and watch them. There are plenty of them where you can educate yourself in different fields of applications. So thank you a lot for your attention. I'm very happy to answer any of your questions if there are some.
I've been using several different microscopic techniques in, let's say, last 20 years, from, let's say, light microscopy to fluorescent microscopy, and also scanning electron microscopy. Everything started with my master degree at Virginia Tech 20 years ago, when I researched penetration of adhesive, urea formaldehyde adhesive into beech wood. And I'm going to share with you some results from that time, but also over the past 2 decades, I've been working on several other projects, and I also include some of these results also. This is the overview of my presentation. Short theoretical part, and then experimental, mostly focus on fluorescent microscopy with different wood-based materials, either solid wood or plywood, so veneer, and then methodology. And I will show you some results, especially focused on adhesive penetration and how this relates to strength or adhesion of adhesive bond. So let me start with the theory. Bonding of wood is, let's say, quite complex process. In some cases, it's easy and simple, but in other cases can be quite complex and complicated. We know that wood is a natural material. It has certain characteristics related to the origin. On the other side, most of adhesives we use nowadays are synthetics. Of course, there are also natural adhesive, but less, let's say, used in adhesive industry or in wood-based composite industry. Next thing which is important is that wood is originally more polar material, especially when we freshly prepare wood surface. But if it stays on the air, or if it oxidates, or if it's, let's say, contaminated with some substances, it can become more non-polar. Another thing, hydrophilic and hydrophobic character of wood, especially wood which is, let's say, heat treated or thermally modified, becomes more hydrophobic, which can present some let's say, difficulties in bonding process. Also, heterogeneity can be a problem related to bonding, and anisotropy, so different properties in different directions. Hygroscopic character can be important. Wood absorbs water in a moist environment, so it will shrink. This can impact also adhesive bond strength. And main point which I'm going to focus today is porosity. So wood is porous material, and this porosity plays a quite important role in adhesion. Main mechanisms for adhesion in wood are actually chemical bonding, physical attraction, and mechanical interlocking. Today, I'm going to focus on mechanical interlocking. This is related to porosity of the material. So adhesive penetrates into lumens and cracks and other pores in wood. And then when it hardens, presents kind of mechanical bonds, anchors. And this way it holds together two pieces of wood or veneer or other wood particles. So adhesive penetration in this, let's say, aspect is very important. So it provides mechanical interlocking, and also it has major effect on bond strength. Here you can see one graph, so tensile shear strength versus penetration depth, and you see that it will increase with the penetration depth, but of course there are some limitations. In practice, there is, let's say, optimal depth of penetration, which assures maximum bond strength. Another function of adhesive penetration is also filling the gaps and lumens. Also, it can assure or provide some secondary interactions, so between molecules of adhesive and molecules of wood. Next function is reinforcement of damaged wood cells, especially, let's say, in peeled veneer, where we have, let's say, late checks and cracks. So adhesive can reinforce those problems. And penetration has impact on wetting area, so it increases this wetting area. And also it provides more effective distribution of stresses. But we need to be careful with, let's say, excessive penetration, because it may lead to starved bond lines. Main factors that influence penetration are adhesive properties. I'm going to discuss a little bit about this on next slides. Then wood properties, and of course, processing variables, especially assembly time, open assembly time and close assembly time. Then press temperature has a major impact. Also pressure. Pressure is actually driving force for adhesive penetration. Time and technology. In these terms, I would like to mention conventional hot pressing in respect to, let's say, high frequency or microwave heating, where adhesive curing is quite faster and different than in case of conventional heating. Some details, how viscosity impacts effective penetration. So if viscosity increases, so it's less fluid, normally it means that adhesive will penetrate less. So you can clearly see in this table that with higher viscosity, effective penetration decreases. Also, resin solids is important, because more solids, less mobility, less fluidity. So it's more difficult for adhesive to penetrate. Or molecular mass or molecular weight distribution is also very important. Small molecules can easily penetrate into wood, big molecules not. Here you see a few, actually two microscope pictures of scanning electron microscopy. You see that a lot of adhesive shrink during the curing, In general speaking, let's say half of thermosetting adhesives is water. So this water evaporates during curing, and adhesive will shrink. On this left hand side photo, you see opening which was created later when adhesive cured and shrinked. Or on the right side, you see crater. This is actually air bubble inside of adhesive, which is in the vessel of beech wood. Then wood anatomy has important influence on adhesive penetration. So which direction, and also whether we have a soft wood or hard wood, then late wood, early wood has impact, and so on. Some species with different wood anatomy and with different porosity and density. First one is Royal Paulonia, very low density, about 200 or a little bit more kilograms per cubic meter. Yellow poplar, 350 to 400 kilograms per cubic meter. Or beech, Fagus sylvatica, almost 700 kilograms per cubic meters, and southern pine about 500. So different porosity, different density, different anatomy or structure also impacts the adhesive penetration and distribution. So now I will turn to one experiment where we used bright field and fluorescent microscopy. Let me tell you that some of adhesives we use, like phenolformaldehyde, it's easily to see under optical microscope. But some others, aminoplastic adhesive like urea formaldehyde or melamine formaldehyde, or on another side, other adhesive like isocyanate adhesive, those are transparent when they cure, and practically you don't see it under bright field optical microscopy. Here you see two photos, and on this left one, you cannot actually detect where the adhesive is. If you use fluorescence microscopy, you can easily detect those adhesive spots. So today, I'm mostly going to talk about fluorescence microscopy. Nevertheless, that we also use electron microscopy and in some cases also micro X-ray tomography. Some details about materials. We used veneer of beech. So we made plywood with different moisture content. Let me explain you later on why this was important. Then another part was a solid beech wood, different orientation, radial and tangential, and adhesive was urea formaldehyde. So this one is transparent when it cures. And now three different experiments. First one was with plywood. So we wanted to see how moisture content of the veneer impact the penetration and curing of adhesive. So at 5 different moisture level. Second one was focused on influence of grain direction on penetration. So either radial direction or tangential direction of penetration. And the last one was actually influence of time on penetration. I could say open assembly time. So we applied adhesive on the surface and we took sample after 1 minute, 2 minutes, and so on. So here was no application of pressure, and of course penetration was much smaller than in case of bonded samples in the hot press. So in this part, we used fluorescent microscopy. The main challenge was how to prepare microscopic slides to see something under microscope. So we use sections with thickness 40 to 60 millimeters, micrometers, I'm sorry. Especially with plywood, we had some problems because plywood is much more fragile and a lot of cracks. So we had to take thicker sample. So then we stained those samples in different stains like brilliant sulfaplavine and safranin O. And then we prepared microscopic slides, and we use epifluorescence microscopy for analysis. This is the examination of adhesive penetration in two different ways. One was so-called effective penetration, which is actually equation which put all those areas of adhesive spots together, and this is divided with the width of the observed image. So effective penetration is much smaller than compared to maximal penetration. Maximal penetration in a simple way is actually the deepest penetration of the adhesive into cell lumen. But because there is high variability, we took 5, the deepest spots, and then made average of these. So so effective and maximal penetrations were ways how we analyze or evaluate the adhesive penetration. And at the end, we wanted to correlate this to the shear strength. We used standard for plywood with some modifications. Here you see specimen for plywood shear strength test, but since we were focused on correlation between adhesive penetration and shear strength, we made a bit different specimens. You can see it here below. So it was cut to the adhesive bond line, and this was the bond line which was also investigated in terms of adhesive penetration. So in this case, we could focus on the same bond line which was analyzed by microscopy, and also failure, or let's say test, shear strength test was focused on this bond line. So let me start with some results. First, some observations. When you analyze adhesive penetration into wood and you prepare your microscopic sections through this procedure by cutting microscopic sections, you need to rinse your samples in water and different alcohols. So I just would like to say that this can impact your results, because some adhesive are not resistant to water. They can, let's say, be impacted with this procedure. So this needs to be taken into consideration. Main let's say, challenge was how to prepare, how to stain those samples to see something under microscope, to see, let's say, high contrast, what is adhesive and what is wood. And then we use image analysis software. There is also quite a lot of variability. It depends on the person who take measurements, how he or she decide what is the, let's say, threshold for adhesive and for other material like wood, tissue, and so on. And last one, there is really high variability in adhesive penetration. We analyze only, let's say, a bit more than 1 millimeter of the adhesive bond line. So we repeated those measurements many times. I think it was 12 times to, let's say, take in consideration this high variability. And now I will show you some results on effective penetration of urea-formaldehyde adhesive versus moisture content. Blue line is conventional hot pressing, and the red line is high frequency heating. So for high frequency heating, you can say, and you can see that actually there is no significant differences in adhesive penetration in regard to moisture content. And this was actually quite logical to explain, because when you use high frequency heating for curing, adhesive starts to heat up immediately. And what is more important, adhesive will heat up more intensively than wood. And in this case, moisture content of wood doesn't play any important role. And as you see here, it's almost line, no differences between different moisture content. But blue line, which present conventional heating, you see that there are differences in adhesive depth penetration. The smallest was at the lowest moisture content, and then we reach maximum at, let's say, medium moisture content, about 9 or 10%. And so the main reason for this behavior is that very dry wood will absorb water from adhesive bond quite quickly. So adhesive will lose mobility when water goes out. And so penetration is not so deep. If you have enough moisture content in wood, but not too much, then penetration will be, let's say, maximal. But with higher moisture content, it started to decrease because wood is not anymore so dry, it's more moist. So this attraction force is not anymore present, but moisture which we have in adhesive bond allows adhesive to move, to penetrate. The same results we got in terms of maximal penetration, also only scale is the difference. So here we have like 40 to 60 micrometers. Here it's around 300 micrometers. But relation in regard to moisture content is practically the same. Also some photos, you see actually visually that there are big differences in the penetration into each wood. So here just few cells, a few lumens, but here maybe 5, 6 lumens in depth. Few other observations. It is important on which surface you apply adhesive. On bottom, let's say, surface where you apply adhesive, adhesive has longer time to penetrate. So typically it's deeper penetration than on the top side, where adhesive only, is transferred when we put together 2 pieces of wood and when we place it into a hot press. There is also a difference in radial and tangential direction of penetration, especially in radial was a bit lower than in tangential direction. Main inhibitor for adhesive penetration was late wood. So in case, as you see it in this photograph in the middle, adhesive actually concentrate only in adhesive bond line. It cannot penetrate through this dense, less porous late wood. You see here some adhesives, but these came along lumen cells or lumen from wood cells. Wood was probably cut under certain angle, and so this adhesive here came from the bond line, let's say below a few let's say millimeters below. In the case of tangential penetration, late wood also has some influence, but of course in this early wood, penetration is quite easy. Penetration in radial direction in the middle can be also promoted through rays, but in case of tangential, it goes through pits between two vessels. I'll show you one detail later on. Here is the results on adhesive penetration versus time or assembly time. You see that most of penetration occurs in the first minutes. So first 3-4 minutes, most of penetration, like 75% of penetration occurs. And then it's normal that it doesn't go further because typically after several minutes, adhesive becomes dry and less mobile, so it cannot penetrate anymore. Also, what is important here, effective penetration is quite low, let's say 4 to 8 micrometers. Before we saw like 40 or 60 micrometers. Main difference here is that here we don't use any pressure. So it was only applied by a roller on the surface of wood, and then we estimate that adhesive penetration without any pressing. Let's see how this depth of adhesive penetration correlates to the adhesion or adhesive bond strength. So on this graph, you see shear strength, which we measure with plywood, and adhesive penetration, so this maximal penetration. You see the best results were achieved with highest adhesive penetration. That was at moisture content 4 and about 6%. And then it started to drop. So it means if adhesive goes too deep, we get a starved bond line. So it's not good to have, let's say, too deep penetration. In some special cases, we have over penetration, like with thin veneer, adhesive comes out of, so through the thickness on the surface. So this certainly does not help to the shear strength, and additionally has a quite bad look or decorative appearance. Another results that was for conventional gluing. This is for high frequency gluing. Almost the same results. Again, we got some kind of maximal shear strength at penetration depth of about 300 micrometers. So if adhesive goes too deep, shear strength starts to decrease. Some conclusions. So in terms of moisture content, there is certainly a significant impact of moisture content on adhesive penetration when we talk about conventional hot pressing. Maximal penetration was detected at medium moisture content of 9%. However, there was no any influence on adhesive penetration in case of high frequency heating, because this is quite a different way of heating of adhesive. Then adhesive penetration was greater in tangential direction and compared to the radial direction. And last one, the pressure is actually main driving force for adhesive penetration. So this also needs to be taken into consideration and control when we analyze adhesive penetration. And main message from this research is that there is an optimal adhesive penetration depth into wood, which results in the maximal shear strength of the adhesive bond. And in case of investigated uraformaldehyde adhesive, this was about 0.3 millimeters one side. So altogether would be a bit more than 0.5 millimeter. And with this, I thank you for your attention. Last comment is here. So penetration through pit, you can see this yellow fish. It has tail in another lumen. So it goes through cell pit opening, but this is not the case in many adhesives, only with a low molecular weight of adhesive. Okay, and this is really all. So if you have any questions, I'm welcome, or happy to answer.
So I will present you some information about this special technique that we have at the Thünen Institute in Hamburg. So the cellular UV spectroscopy is based on the electromagnetic spectrum, especially in the range of the UV light. So Here you see the range between 200 and 400 nanometers, and our device is able to go up to 700 nanometers. So we also reach the visible light. And the principle based on this technique is the transmission and interaction of the UV light with the sample according to the Lambert-Beer law. We heard already something about John Heinrich Lambert in the DIC presentation of Václav. So here we got the combination of Lambert and Beer. And it says that we got A as the absorbance UV light that comes from the cell wall due to the absorbance of lignin. Then we have the extinction coefficient and the volume connection, as well as the thickness of the absorbing layer. So when we transfer this principle to the wood cell walls and the wood especially, we talk about the intensity that is measured by passing through the embedding medium through the cell lumen. So it's called I0, and the energy that is passing the cell wall layers. And we got this equation, the basic equation from the Lambert law, and we got this information about the absorbance A, and it's derived from the logarithmic value of the emerging intensity from the lumen divided by the emerging intensity of the cell wall. These are the physical backgrounds. And now we have the sample preparation. You already saw some nice pictures by in Anna's presentation. Here we have the sample size. It's about 1 millimeter to 1 millimeter in the cross section, and then about 5 millimeter length. And here we have a picture of the vacuum embedding in the epoxy resin according to Spur. So it's a very mild embedding system. You can use this one, or you use capsules. And then you have to use an ultramicrotome to prepare the semi-thin sections of about 1 micrometer thickness. Afterwards, the sections were mounted on quartz slides, and the result looks like this. This is an overview picture, and we stain it. So we get a nice overview of the cells we want to look at. And then we put it into the device. So this is the universal microscope spectrometer. It looks like a microscope, and you get UV light that transmits through the sample. This device is able to scan areas, and here we have constant wavelengths. And these, it depends on what you want to look at. If you have a softwood or hardwood, you use the maximum of absorbance for lignin. In softwood, it's about 280 nanometers, and in hardwood, it's 278. This device is able to have a very high geometrical resolution, about 0.25 micrometer to 0.25. And the photometric resolution is about that we detect 4,096 grayscale levels. And these grayscales were converted into 14 basic colors. It's seen on the right side. So 14 colors. So we get really nice pictures in that can be depicted as 2-dimensional or 3-dimensional image profiles. And these were also statistically evaluated in a semi-quantitative lignin distribution. So with this device and this equipment, we are able to visualize the lignin distribution in the wood tissue. And we are also able to show the lignin concentration. Another tool is the point measurement. So we can just look at individual cell wall layers. Here we use varying wavelengths in the range between 250 and 420 nanometers for the cell walls. And when we want to look at extractors or other things within the parenchyma cells, for example, then we choose a little bit higher wavelengths up to 600 nanometers to get all this information in the wood. Here you see the spot size. So yeah, we're able to analyze even just the middle lamellar or the cell wall corners represented by the red dots, the stew layer, or even the the deposits in the cell lumens. With this equipment, we have the possibility to analyze the spectral behavior of different cell wall layers and the deposits. So the application possibilities, I will present you three different projects where we used this technique. You have already seen the project of Anna, where we want to look at the tannin distribution in the impregnated wood. The first thing I got in touch with this method was in my diploma thesis. I had the chance to look at waterlogged wood after 100 years. It comes from the Panama Canal. And there was, during this construction from the canal, a very large area has been flooded, I think so. And it's a very big, large area, and they didn't cut all the trees. So the trees are still fixed in the ground, and yeah, so they are still there, and now they can be harvested, and there are a huge amount of different tropical species as Masaranduba, Kumaru, and Andiroba. Andiroba is comparable to mahogany, so it's a very valuable wood. And here we got the question, are there any detectable changes in the topochemistry of the wood cell walls? And yeah, we prepared the samples and we had a look at the ground tissues, the fibers. And this is the result we get from the UMSP. On the left side, you see the two-dimensional picture, and the bigger one is the three-dimensional. And here you see the concentrations of the lignin. We have a highest concentration in the cell wall corners, and it decreases to the cell wall lumen. So that looks pretty fine. And after 100 years in the water, nothing happens to the cell wall structure. So we have very nice wood that can be used. Yeah, that can be used for indoor applications. What else do we want to know? What about the point measurements of this individual cell wall layers? Here we got, oh, I'm sorry, it's in German. Here we see on the x-axis the wavelengths, and on the left side, on the wire layer, the extinction. And the maximum absorbance occurs around 278 because we have a soft hardwood species, and that occurs in this region. And we see the highest absorbance intensities are measured at the cell wall corners, followed by the S2 layer of a vessel. And here's the highest absorbance for the combined middle lamella. What else we want to look at? These are the deposits in the parenchyma layers. So we wanted to know if anything changed here in the composition. So the parenchyma is depicted in the red line, and these are located in the lumen of the cells. So they are not impregnated. We have them just in the lumen of the cells, especially in the parenchyma cells. These are aromatic compounds, and what we detect are the chromophoric groups. And these compounds are responsible for the nice color of this tropical wood species. The next one is, for example, the fungal degraded wood tissue. Here we are looking for initial decay pattern and what happens to the lignin. Rehbein and Koch investigated Pinus sylvestris, and it's degraded by brownwood fungus and Rhodia violante. And the two-dimensional picture shows you with the arrows several areas with lower intensities, so the brownish one, and some areas with higher absorbance intensities. And it also can be depicted as a three-dimensional graph. And you also see the histogram that gives you the statistical evaluation. That means during the wood decay by brownwood, the lignin is modified, and that's why it changes its absorbance intensities. And this is very nicely shown with this technique. And the last example I would like to show you is the furfural alcohol modified wood. So it's my topic of my PhD thesis that I finished now. So we want to know, is it possible to use this UMSP technique to investigate this furfurated wood from the infrared results? We know that it has a very high fluorescence properties. So we had to adapt the technique and change the thresholds, and afterwards we get really nice pictures. This is the untreated radiata pine, and this one is the treated one. So when we compare both pictures, you see a clear difference from the pink reddish pixels to the green ones. So we have an intensive modification of the whole cell wall layer shown by these high absorbance values. So this technique is absolutely great for investigate this impregnation and how good the cell walls are impregnated. So I just put everything together for a quick overview about the cellular UV spectroscopy method. We have a topochemical, we are able to characterize a cellular level of specimen. It's a highly sensitive method with a high spatial resolution. And the very special thing is that we have an in situ characterization. So you have the wood tissue exactly at that point where you want to look at. So you don't destroy everything and just look at single components. You have just the wood tissue as it is, or as it was in the board or in the larger sample, and you can look just at this point. So you are able to analyze fungal degradation pattern. You can analyze lignification, delignification, or lignin modification. So it's also very valuable for investigation of the wood formation. There you can follow the lignification of the cell walls. And as we saw for the furfural alcohol, as well as for the tannin, we still have to evaluate this. It's possible to analyze modified wood. The disadvantages are the elaborate sample preparation. So it's very takes some time to prepare the samples, and you just have a small window you open and look at a very special size of your specimen. So it depends on the research question if this method is useful for your analysis. This was a short overview of the UMSP technique, and you're welcome to ask any questions now or via email. Thank you.
So first of all, I would like to give you like an insight on which length scale we're working on. So when we zoom into a wood cell wall, we see the different wood cell wall layers, and we see a like really precise organization of the wood components. And with atomic force microscopy, we are able to really capture the smallest components of wood down to the cellulose fibril aggregates. So we can really capture the wood nanostructure and can really take a look into the smallest wood components. And as we heard before, we have like certain challenges when we work with wood. It is porous and it's natural variable. So we really have to like prepare our samples in a way that we overcome these challenges. And yes, we also have like the hierarchical characteristic of wood. So on different length scales, we have certain arrangements of the wood components. And so we always have to like specify on which area we are doing and performing our measurements. Yes, so in wood characterization, we can in general specify if we're looking at chemical information, or if we looking into more microscopy tools where we have very high spatial resolution. And when we compare different methods, we have like infrared spectroscopy, we have Raman spectroscopy and Raman mapping, and we also have like tip-enhanced Raman spectroscopy. And when we look more into the techniques with high spatial resolution, we can look at optical microscopy. We already heard a lot about electron microscopy, like scanning electron microscopy or transmission electron microscopy. And yes, I am focusing on atomic force microscopy. And the goal also of my PhD thesis was to fill a little bit this gap in between these microscopy techniques, so we can get chemical information in combination with high spatial resolution. So we can really follow the nanostructure of wood materials, but also that we can get chemical information of these nanostructures. And yes, to give it a little bit of a general overview about these microscopy techniques, I just took my own hair and I captured it with different microscopy techniques. And we could see like in light microscopy and in electron microscopy, we get like a nice image of the general topography. And then when we take atomic force microscopy, we can capture the smallest components out of our material. And here it's really important to note that atomic force microscopy, we take it for like a nanometer and like micrometer structures. And we really have to have like a flat substrate, and we cannot, for example, measure the whole cross section of a human hair because it's just too big already for atomic force microscopy. So really we need to take into consideration that we always measure small components of our material. And yes, so the principle of atomic force microscopy works with a tip. So we have a tip with a radius of some nanometers, and this tip is scanning the sample. And we're tracing the movement of this tip with a laser system. So we can precisely follow how this tip is scanning our sample. And we have different modes in how we can measure this. In one mode, the tip is always in contact with the sample, which is called the contact mode. And in the other mode, the tip is oscillating and has like a really small interaction with our sample. I will talk about this in more detail in the presentation later on. And with this setup, we can get into the smallest features of our sample because the tip has a radius just of a few nanometers. So the tip is very small, so it can get into the smallest features of our sample. So here you can see like how an AFM image is generated on a wood cell wall. So we have our prepared wood sample. We scan the wood surface with our tip. The tip is carried by a cantilever. You see it here, like the triangle, like moving to the left, to the right in the left image. And the cantilever carries on the bottom side the tip. And you can also see on the left image, you can see the laser system, which follows the movement of the tip and precisely captures the movement of the cantilever that carries the tip. And then line by line, you see it on the right side, we generate our image and we create certain false color image, which you see on the bottom of the slide. So this false color image gives a representation of the topography of our sample, and is generated in a way that high points will get a bright color and dark points will get low points will get a dark color. So we always have to take care that this is really a picture generated by the movement of the tip, and it's not like an optical image of our sample. And we really have to take care that we have here like false color images, which are just generated by giving a color code to our height position. So just to repeat, a high point in the line will give a bright color in the image, and a low point in the line will give a dark color in the image. So when we're looking into like wood cell walls, we can distinguish nicely between different components of wood cell walls. We can see the secondary cell wall. We can nicely see middle lamella. We scanned here a little bit into the lumen side, but we have to take care that we're a little bit limited with the movement of the tip. So the AFM that we have available at our institute, we can measure in XY direction, like in the image size, we can measure up to approximately 100 micrometers. And in Z direction, like into this height code, we can measure like maximum up to like plus minus like 6 micrometers. So we're really limited in a way that we have to have like flat substrates for our measurements. And then the powerful thing about atomic force microscopy is that we, when we zoom in into our sample, like here on the right side, you can see the image of like a zoom image into the secondary cell wall. We can already see the wood fibrils, like with the resolution of like several nanometers. Like I think this image has a resolution of like 2 nanometers, and we can like nicely measure components like the wood fibrils of about 30 nanometers. So here you can see what the advantage of atomic force microscopy is, that with little sample preparation, we can already get a really high resolved image of the wood cell wall structure. And to prepare such samples, we need to microtome them. So in the first step, we take some small wood pieces out of our material, we glue it onto these metal discs, and then we can cut them with diamond knives. So we have very sharp knives, which deliver the needed flat surface for our AFM measurements. And then before we perform the AFM measurements, we select suitable cellular layers with light microscopy. So as we know, wood is very variable and has like a lot of artifacts. We first need to check in a light microscope if we have like flat measurement positions, which we can use for AFM measurements. And then we can perform the AFM measurements with our setup. And then we get these topography images. So here I use the software Gvidion, which it's a free software where you can nicely analyze your AFM data. And we can distinguish between the cellular layers and the lumens. And we also analyze a lot the adhesion forces. So the adhesion force is the force that we calculate out of the tip movement when the tip is not in contact mode, but the tip is in like a tapping mode. And the tip is always like touching in really low forces our sample. And the force that we need to move the tip back to the previous position after it touched the cell wall, we can calculate the adhesion force. And this is, I will go into detail in this later on, but we always get like in our, in this mapping mode, we get topography information, and we also get like adhesion mapping. So some challenges that we have on wood samples is that we have a certain roughness with wood that is coming from the different arrangement of the wood cell walls. We have variability, and we also have like certain artifacts. And we also have the topic of hygroscopy. So you see one AFM image that we captured in air and one that we captured in water. So we are able not only to perform measurements in air, but we can also perform measurements in like liquid surroundings, which helps us to overcome this, these capillary forces which we have between the tip in air and our wood sample. You can see this in like the middle image on the bottom of the slide. And to overcome these like capillary forces, which happening when the AFM tip is touching our wood sample in like an standard environment, we can make the whole measurements in a liquid surrounding. So we place the sample inside, for example, water, and then we're performing these measurements with an aqueous surrounding. And you can see on this AFM image in water, we can see the wood swelling. And this is very tricky for us because we all like wood is not swelling in one direction the same. We have a lot of like direction depending swelling, and we really have to follow precisely the movement when our wood sample is scanned. And I said before that I tried to, like with our AFM measurements, we tried to fill the gap between like high resolution microscopy and also chemical mapping. And here we have like further developments that we applied on wood materials to kind of fill this gap. And one of them is like chemical force microscopy, where we chemically modify the tip. Then there's a lot of research going on in the moment with combining AFM with infrared microscopy. And also we applied scanning thermal microscopy. So first I want to talk about chemical force microscopy. And in this method, we do not use standard tips, which are usually made out of like silicon nitride. We're using chemically modified tips where we attach certain chemical components which end in a specific functional end group. And then we can set the surrounding to the opposite polarity. For example, we're measuring with a hydrophilic modified tip in like an hexadecane environment. And we can also do the same thing, which like modifying the tip with a hydrophobic functional end group, and then we perform these measurements in water. And then we again looking at adhesion maps. So how much force we need to move the tip back to the previous position after it touched our sample. And these adhesion maps, they're also captured with this really high resolution. So every time the tip touches our sample, we're recording a structural information and also this adhesion map. And so, for example, here we're scanning the cross-section of different cellulosic fibers, and we could see that the adhesion force is really depending on the composition of the cellulosic fiber. And we could map with high resolution not only the structure of these fibers, but also the polarity of these individual cellulosic fibers. So one of the fibers contained some lignin, one of the fibers did not contain lignin, and others had like different compositions, and we could really follow the polarity changes depending on the composition of the fibers. And a different method that we applied to also do this chemical mapping, it is called peak force infrared microscopy. And we did this in cooperation with Xiaoxi Zhu. He's working at Lehigh University. And he developed this setup where you have this AFM tip scanning your sample, and therefore will deliver us high resolved images of the wood cell wall. But in the setup, there's also a laser which is focused between the tip and the sample. And due to the laser, we have like thermal expansion of our sample, and we can measure this thermal expansion with the AFM tip. And this thermal expansion is depending on which chemical component is mapped between the tip and the sample. So we can not only measure the height information of our wood cell wall, but we also get chemical information based on the thermal expansion, which was driven by the laser, which is focused between the tip and the sample. So this is results of the measurements on a wood cell wall. So here you see like the section of a secondary cell wall of spruce wood. And then you can see like we can measure this like height information. And on the right side, you can see that we also get like this infrared signal when the laser is tuned to a certain wave number. So here we have like the laser tuned to 1026, and we see where chemical components are situated, which have like thermal expansion at this wave number. And we can also map adhesion and modulus because the tip is in this mode, it's in peak force tapping, as the name already tells us. And in this peak force tapping mode, we can also deliver adhesion for information and also information about the elasticity. So we also get information as modulus when the tip is in the oscillating movement and is touching the sample and giving us like typical modulus information by indenting the tip into our sample. So in the one measurement, we can get height information, we can get modulus information, and also infrared signals. And we used this measurement to really get precise information about the wood nanostructure and also to deliver like this chemical information and the precise organization of the wood cell wall. And another technique that we can do with our AFM setup at our institute is scanning thermal microscopy. And in this setup, the tip serves as a resistive heater, and we can measure thermal changes between the tip and our sample. So for example, we performed these measurements on a bamboo cross-section. So we had like a bamboo sample, and we selected certain measurement positions. And then we could measure the topography of our sample. And by also following the temperature changes within our samples, we could also see different thermal conductivity in the cross-section of bamboo cell walls. So what is happening, the tip is set to a certain temperature and is scanning the sample, and certain areas are able to like conduct the heat of the tip, and some areas like have lower capability of transferring the heat. And we can capture that. And so for example, here you can see the different cell wall layers of the bamboo cell wall. And we see that certain cell wall layers have like a good connectivity, and some cell wall layers have like worse connectivity. And we can correlate this back to the different orientation of the fibrils inside each individual cell wall layer. So we have like this further developments of AFM, and there's a lot of research going on in how to modify the AFM setup to not only get nanostructural information, but also to get information such as chemical distribution on a nanostructure, and also to get like information like the nanothermal conductivity of our samples. So we want to use these methods to really confirm and target our modification processes. And we also think that this really helps to the development of different functionalized lignin cellulosic materials. And we're always really looking forward to study new substrates. So we're very happy if you want to collaborate with us and to study your samples also with our AFM setup. Yes, with this, I would like to thank you for your attention, also to thank our financial support. And yeah, feel free to contact us if you have like further questions, and I'm happy to answer your questions now.
So introduction, yeah, Milan already did some introduction about adhesion phenomena and surface phenomena in relation to bonding of wood, and the same is in case of coating of wood. So I won't be here too long. So let me just say that surface phenomena are quite broad area. Everything is mostly related to these three areas, let's say. So that's the chemistry of wood surface, the physical properties, mostly the surface free energy of wood surface. And in this presentation, maybe I will more be focused on the morphology of the wood surface, which we can monitor and observe with microscopy techniques. Speaking of wood coatability, there are many parameters which influence the wood coating relations and the interactions. So the first are, of course, coating properties, physical, chemical, and so on. The next one is wettability of the wood surface by the coating, how the coating is spreading on the surface or spilling, how deep the coating penetrates in the wood structure, and then everything affects the mechanical anchoring and adhesion of the coating, and so on. I will start with the methodology presentation. First, everything is based on the preparation of the samples which we want to observe. There are many ways how to do it, how to prepare the surface of wood. One is simply mechanical, like solving, planing, and sanding, but these are not the proper methodologies to have it for later observation. Mostly I'm using the cutting on a sliding microtome, which we can see on the photo. This is, of course, the destructive method, but makes the surface very smooth and proper for observation. Another more sophisticated techniques are some laser and ion beam irradiations, but up to now I didn't use this, but they are possible to be used. Another thing is the preparation of the coated samples. We can do this in two ways, either cutting the samples before coating, like in this case on the photo above, or cutting the sample after application of the coating. So there are two approaches. It depends on what do you want to see and how do you define your expertise. Up to now, I used different techniques for observation of the coated wood and interfaces. First are optical imaging, and one of these is either digital or simply light microscopy to observe the surface system. I show here a few cases of a light microscopy, either using a digital microscope, like in this picture, or the simple light microscope, to determine the, let's say, roughly determine the, for example, the coating thickness and the layers between the coatings. Also with digital microscope, we can do some 3D scanning and then do the 3D images like we see on the right below, one example. I consider also like microscopy if using for determination of wettability or measuring the contact angles of the liquids on the surface of wood, because also here we are using actually digital camera and by certain magnification, and I can say that we can also consider this as a microscopy, using it for studying the wettability or coatability of wood. The same is in case of doing the experiments on tensiometer, by dipping the samples into the liquid, like slices of wood into the liquid, and then observing the phenomena like meniscus, how the meniscus between the liquid and the sample is formed, its height and radius and so on. Another usage of light microscopy can be also to monitor the wettability or the spilling of the droplets after application on the surface of wood. Not only again measuring the contact angles, but the spilling area, measuring the area on which the droplet is spilled after the application during the time, of course. Here on the right side, we can see an example of how in this study, the the microscope was positioned above the sample where the droplet of the coating was applied. Under optical imaging is also the confocal laser scanning microscopy, which we do have in at our department. Probably you know this technique. It's nice to use it for imaging the 3D structure of wood or any other surface. We can see two pictures of spruce wood and beech wood. Above, right below is some indentation on the coated wood with some other equipment. And on the left below, we see again an example of measuring the coating thickness on the 3D printed material. Another application of confocal laser scanning microscopy can be the damages which were done by using the micro scratching technique to determine either the width of the scratch, its depth, and so on. So to evaluate the resistance of a certain coating system or surface system to scratching or some other influences. Another technique is a scanning electron microscopy, which we do have at our department. We see the photo here, and one photo of the sample which was used I think for determination of penetration depth and the coating thickness. The sample must be properly prepared, as I said, like before on the sliding microtome, and also spattered with the gold for better conductivity. Some examples of non-coated wood but exposed to artificial weathering on the left side. So the same area, different spots before artificial weathering and after artificial weathering. So we were observing here what's happening with the wood tissue when it's exposed to light and humidity. And same on the right side, after doing some plasma treatment of wood, I was observing some changes in the microstructure of wood, of beech wood in this case. Also using scanning electron microscopy on the coated wood. On the left side, we see 3 images from the surface, some artifacts on the, I won't go into detail too much. And on the right side, again, using it for measuring the coating thickness and yeah, also the penetration depth. Here we see some scratching, like I showed before on with the confocal laser scanning microscopy. This time the same scratches were analyzed with the SEM. So what's happening with the coating in detail on the cross section on the surface. So we see some damages. And on the right side, we see 2 images. Above is before artificial weathering and below after artificial weathering. How the damage on the coating of wood, of the coating film is happening or is observed from the surface. 2 examples using scanning electron microscopy for determination of the coating thickness on either normal wood above and densified wood below. Besides that, after the densification, the structure of wood is completely, let's say, different than before. Also, the coating penetrated less into the surface because of the denser substrate. Let's say it simply. By using the scanning electron microscopy and using different detectors, we can also distinguish between the elements in the coating, like we heard in the first presentation. Also, here is one example with one detector, we can see clearly for example, some pigments, another inorganic elements in the coating, and with the other detector, maybe some more morphology or these things. The third technique which I was using in this case in Ghent University is X-ray microtomography. Again, here we were studying the penetration of the coating inside the wood. On the left side, we can see the photo of this equipment. Probably you know it. I won't go into the details. And on the right side, we can see the sample prepared for the analysis or the scanning. It's very small and needs to be properly prepared. And yeah, for that we are really precise and the results are the proper ones. So after modeling the scanned samples, we can see on the left side the image of such sample. We were focusing on the interface between the coating film and the substrate, and on the right below, how we were, let's say, distinguishing between the coating and the wood. I can say it's quite challenging. We can use some, let's say, elements which could be added into the coating to get better contrast between the coating and wood. But anyway, we were reslicing these 3D models of the scanned samples, and then using simply image J, we were detecting or measuring the porosity versus the tangential distance from the surface inside into the sample. So here is the result, for example, how the presence of the porous structure is increasing with the tangential distance into different wood species. Yeah, so this is one example how we did it. We could do it also other way, but in this case, we were using this approach. So to conclude, as said before, surface phenomena does affect the coatability of wood and wood-based materials. So we are speaking of surface and coating interactions. Here are important the surface morphology which we can monitor and observe with different microscopic techniques. Also the porosity, some anatomical features, and so on. And for studying the coatability of wood, we can use various microscopic technique, but it depends on the information which we are interested about or which we want to see. What is the magnification of interest? Of course, we can use different techniques, but it depends really how deep into the material, let's say, you would like to go. Of course, everything depends also which equipment is available to us and how the sample preparation methodology and so on is complex, and also the cost of the studies are also the limiting factor most of the times. So everything then affects the end properties of the coated materials, like adhesion and so on. At the end, I would like to acknowledge to our research agency and to Wood Plus project for this opportunity to give you my presentation, and also to all of you for your attention. Thank you very much, and questions, please.
In this presentation, I will tell you something about electron microscopy in our Faculty of Forestry and Wood Technology at Mendel University in Brno. I will focus on modified wood, and I will show you some Sample preparation. My presentation will be mostly focused on sample preparation and some examples of our research. First, short introduction. You need a piece of wood or modified wood for this microscopic technique. First step is making smooth surface using microtome. Next step is mounting on aluminum stubs. Then the samples has to be coated with gold and to make the sample more conductive and avoid charging during microscopy. And the last step is electron microscopy. Just a short introduction, and now let's go to the methods. Sample preparation. It's crucial for the result quality. You need a really good surface for good images. Down on the screen, you can see 3 examples of beach. On the left side, it's good images. The sample was very smooth after cutting. In the middle, you can see some problems with cutting. There are some damaged parts which were created during cutting. And on the right side, you can see a lot of damage due to cutting. To get good surface quality, there are some steps we need to do properly. First step is softening. Good softening means better cutting. It also depends on the material, if it's possible to soften due to material or research aim. The next important thing is a sharp blade. It means if you need a really nice surface, you need to do the last cut with a fresh blade which has never cut before. And very important is also cutting angle. I will show you more on the next slide. And also, thickness of the shaving can influence the surface quality. If the shaving is too thin, usually the surface is more damaged. During cutting, there are some angles, like shown on this picture. I use this Leica / microtome. There are some possibilities to set the angles, and I will show you. If you have a big cutting angle, which is delta here, then the shaving is more bent, more pushed or compressed, and there is a higher possibility to damage the surface. So the cutting angle or the clearance angle should be very low, very small to get good results. Problem with microtome is that the clearance angle is quite big and cannot be set smaller. You can see detail on the right side. There is a detail of cutting blade in microtome and the sample. You can see the holder prevents me to set a lower clearance angle. This drawing you can see here is with the exact angles, the same angles as on the photo on the right side. There are some options how to decrease the angle. We cannot set a lower clearance angle here because of the holder. There are some other options. we can use transformation of the angles. If we set this angle of the holder this way, as I showed you with these red lines, this angle can help to transform the cutting angles, and the result is the angles are smaller. I can switch again. This, look at the drawing now. You can see the real angles when it's perpendicular. If we set some angle, let's say 45 degrees, the transformations makes them smaller. There's not a big difference, but there is a difference. So this decreasing of these angles can help to make smoother surface. Unfortunately, this microtome doesn't allow to set the angles even lower, but there is another option. If I want really a very good surface, I simply use the hand cutting with razor blade. It allows me to make the clearance angle practically to be 0. I can't make, of course, a big surface with such a razor blade, but for the electron microscopy, small, smooth surface is enough. Let's go further. There are some challenges with sample preparation. If we want to cut smooth surface, we can the problems could be too hard material. For example, it could be impregnated material or a densified material, or the material is too soft, like decayed material, or some particle boards or composites can be very soft. It could be a problem. And also, if the sample doesn't soften in water, it's hard to cut smooth surface. In case of acetylated wood, there is a possibility how to do it. Acetylated wood doesn't soften in water, but it can soften in acetone. So there is a way. But in case of impregnated material, sometimes the resin doesn't soften in water, so it can be very difficult to make a smooth surface. And there are also could be also problems with sputter coating with gold. It is needed for the electron microscopy to get good resolution and no charging. You can see on the image on the right, there is a lot of charging, the white parts. This was a sample which was broken in some small bending test. And I want to see the broken surface. And even after a thick layer of sputter coating, there was not enough to conduct the charge away from the sample. So there is a lot of charging, and which destroys the image, the result. The other problem with sputter coating could be volatile compounds. If we have impregnated material, there could be some volatile compounds, could be some low volatile compounds, but still, if there are some, it could influence the position of the gold during sputter coating. You can see this stub with a very small wood sample, and you can see the stub is very well coated with gold, but the layer of gold on the sample is very poor. The solution for this problem is either remove the volatile, or good solution is to make the sample as small as possible. It helps with charging in in any case. Also, in case of rough surface, if the sample is smaller, the charging is lower. In this case, the sample is about 2 by 2 millimeters and about 0.6 millimeters thick. The layer of gold was poor, but it was sufficient to make some images. Now, I will show you some results from my electron microscopy. First example is reference hornbeam and acetylated hornbeam. In this research, we wanted to know how the acetylation influences the wood microstructure. At first sight, I didn't notice any changes. The changes in thickness of cell wall is not visible by naked eye, but after measurement, we could find that there is some difference in cell wall thickness. And the other difference between reference and acetylated hornbeam are these pits. The pits are shown with these arrows. These white arrows show the pits in reference on the left and acetylated hornbeam on the right side. And you can see there is a big difference between the pits. Reference hornbeam has very wide pits due to cell wall shrinkage. And acetylated hornbeam has the pits very narrow. It's due to swelling of the cell wall during acetylation process. So the cell wall is permanently swollen and the pits are slightly closed. We also did some experiment with decay test. And here you can see the results. In acetylated hornbeam on the right side, you can see the fungi is growing there, but no visible damage and very low number of the hyphae. On the right side, you can see wood damaged by the fungi. Coniophora puteana, the image A, you can see significantly thinner cell walls, which was dissolved by enzymes from the fungi. And in case of acetylated wood, the cell walls is intact. So the result is fungi can grow in acetylated wood, but it has difficulty to decompose it. That's why it's a very durable material. Another example is birch veneer bonded with recycled polyethylene. You can see the bond between polyethylene and beechwood, birch wood is simply just interlocking. There is no real adhesion between these two materials. And this is beech impregnated with melamine formaldehyde resin. This resin is very strong, very hard, and difficult to cut with microtome or razor blade. It makes the blade wears out very quickly. You can see different behavior. On the right side, the resin makes such a beads or spheres, and in the image on the right side, the resin makes layers in the fibers, or in this case, these are vessels. Let's go to another example. And this is wood plastic composite. It's a HD polyethylene, which was mixed with milled wood. It was an experiment to utilize a speed milling process. And then the material was compressed in a heated press to melt the polyethylene, which then connects the particles. We can see that the particles make some clusters on the left image, and the polyethylene doesn't penetrate well to the structure of particle clusters. It could be because of high viscosity of melted polyethylene. Another example of electron microscopy, this is beech wood on the left side and spruce wood on the right side. And there is a layer of polyurethane glue. You can see the penetration of glue to the wood structure. In case of beech, which is more permeable, you can see that the penetration is much better than in case of spruce on the right side. You can see the penetration is just maybe two cells. Even if there are some bubbles, like you see some bubbles in or cavities in the bond line, it's still very well bonded together. Presentation. So thank you for your attention. And if you have any questions, please ask me.
Thank you for the introduction. And today I will show you some microscopic technique for waterlogged archaeological wood, and in particular going deeper on sample preparation. At our department, Katarina Schufer and Max Merela with us, they have long experience with this kind of material. And today I will show you some experiment we have done on the 5,500 years old prehistorical pilot dwelling settlement in Ljubljansko-Barje in Slovenia, on some of those samples. This material is very demanding because it is wet, and you see here those are two discs of waterlogged archaeological wood of Quercus. And you see in the first image, this is wet wood. And if you leave it to dry at the air, it shrinks and becomes like almost half of it. So we don't want this, and we have to prepare the sample in the way that they don't shrink when we are working with it. For this is a very demanding material for sample preparation. And today I will show you how we work and prepare this material for light microscopy and scanning electron microscopy, to see the characterization of this wood at different levels. So we will start with the light microscopy. Here you see that we have those samples we store in a refrigerator and under vacuum and waterlogged. Then to make slides for light microscopy, we prepare the sample before cutting it in a small sample orientated, and then we embed it in paraffin. In this way, it becomes harder and easy to cut. Then we prepare the paraffin block, and
we obtain a slide of 9 micron of thickness. Then we have different staining processes. Sometimes we also avoid staining to see different features. And also we include this material in paraffin because I don't know if you have in mind this kind of material, but if you touch it, it has the texture of the butter, so you can't cut it directly under the microscope. Here we have some result. In the first images you see the sound wood of Quercus, so how it looks normally. And here you have unstained section of waterlogged archaeological wood of Quercus, and here a section stained with saffronin and astra blue mixture that enhance the contrast in the cell wall and in the content of lignin. And here you see that you can reach quite high magnification and see also the feature of cells, and in this case you see the cell wall almost disappear, and only stayed the middle lamella still there. Then we used, as I said, different staining. We said the mixture of saffronin and astra blue, but also acridine, chrysoidine that we used to apply epifluorescence on the slide. And this because we wanted to enhance the lignin content in the cell wall, and also to see different details that in unstained section are not visible. And so you see that this kind of sample preparation can make see you different details, and also obtaining such thin section you can get high resolution. But the problem is that such thin sections are also very easy to tear apart. Another technique we try to apply on this wood is the scanning electron microscopy. In this case, it's even more challenging because normally for this kind of sample preparation, we trim the surface of a small cube of wood to make a very flat and nice surface. Then we coat the wood to make it conductive, in this case with gold, and then we can observe it. But with the waterlogged archaeological wood, we have wet wood, and this cannot be inserted in this way in the SEM chamber, because the SEM chamber must be under vacuum, and also it can't, it must be cut in a way that we get a nice surface. So we decide to freeze the sample and to cut a thin slide with the razor blade by hand. And you see here this thin slide that are around 20 microton. They are glued on the stab with the albumin, and then inserted in the oven for 15 minutes at 70 degrees, in the way that the albumin became like a glue, and the section stay on the stubs without shrinking. So in this way, we can observe the wood under the scanning electron microscopy, and you see that we can get very high magnification. We can both have a large image for the identification. In this case, we identified Acer species, and also to get some insight and to see some detail that are usually hard to see, like here in the vessel, these helical thickness, and also the position of those bacterial. We applied also, together with SAM, energy dispersive X-ray spectroscopy, EDAX, for the chemical characterization. As you saw before in the vessel, there are some crystal that we found, and we wanted to identify the elements that were inside to understand which kind of crystal they were. So we applied EDAX, and we saw that mostly those crystals contained ferrum, sulfur, and silicium. And so this was give us the suggestion that is initiating the process of fossilization. So with this presentation, I wanted to show you how it can be difficult to manage the preparation of this kind of material, and which are the possibility that we can get from light microscopy and SEM. But as conclusion, we can say that we should perform both technique, because each of them, they can give us different results that must be combined. So thank you for your attention.